Welcome to information representation. At its core, a computer is just billions of microscopic switches turning on and off. It has no concept of numbers, letters, colors, or sound. In this unit, you will learn exactly how we force those simple on-off switches to represent the entire human experience. This is the bedrock of Paper 1 and the silent engine behind all your practical programming in Paper 2 and Paper 4. If you want to understand how a machine actually thinks, this is where it begins. Everything starts with base 2. You will learn to translate fluently between denary, binary, and hexadecimal number systems. Hexadecimal isn't actually for the processor, it is a vital shorthand for human programmers. You will need these conversion skills to read memory dumps, trace MAC addresses, and secure marks across both theory and practical papers. Without these foundations, the rest of computer science is just magic. Once you can count, you need to calculate. You will master binary addition, multiplication, and how to spot overflow errors. But how do you store a negative number when you only have ones and zeros? You will learn 2's complement, the elegant mathematical trick that makes hardware subtraction possible. We will also cover binary coded decimal, the exact encoding financial systems and digital displays demand when rounding errors are simply unacceptable. Integers are easy, but what about microscopic fractions or massive scientific values? You will learn how computers store real numbers using a mantissa and an exponent. You will normalize these values to maximize precision and evaluate the brutal architectural trade-off between precision and range. This topic is often the ultimate discriminator for top grades in your A-level theory exams, testing your ability to think like a systems architect. To store text, we must map every single letter and symbol to a unique numeric code. You will compare the original 7-bit ASCII standard against modern Unicode. You will see exactly why Unicode was invented to support global languages, and you will learn how to calculate the exact storage cost of any text document. Every string you ever code relies on these invisible mappings. How do we digitize reality? For images, you will break continuous photographs into grids of pixels, calculating exact file sizes using color depth and resolution. For sound, you will slice continuous analog waves into discrete digital samples. You will apply the Nyquist theorem to find the perfect sample rate, balancing pristine audio quality against massive file sizes. This is where mathematics meets human perception. High-quality multimedia creates enormous files. To transmit them across networks efficiently, you must compress them. You will execute lossless algorithms like run-length encoding and Huffman coding by hand, calculating the exact bit savings. You will also evaluate lossy compression, deciding exactly what data can be permanently destroyed without ruining the human experience. It is all about maximizing efficiency without sacrificing meaning. By the end of this unit, you will see exactly how a machine built purely on microscopic switches can process complex math, multilingual text, music, and high-definition video. You will have the exact toolkit required to dominate the data representation questions in the Cambridge 9618 exams. It is time to dive in.